Thermoelectric materials have the advantage of converting heat into electricity and can be used for heat flux and temperature sensing. These technologies are based on the Seebeck effect, which is the creation of a voltage from a temperature gradient. The voltage is generated as a result of the diffusion of mobile charge carriers transported by the heat flux. Another important quantity is the conductivity, which describes the movement of charge carriers across a material as a result of an electric field. Both the conductivity and the Seebeck effect are both inversely related, and the design of a thermoelectric material often results in the sacrifice of one property. Typical ion-conducting polymer systems exhibit unstable ionic conductivities and ionic Seebeck effects. In addition, the microscopic mechanisms responsible for changes in the ionic Seebeck and ionic conductivity are often unclear. The contributions of conductivity from multiple charge carriers are often very hard to track and quantify, as well as in the case of the Seebeck coefficient. Many of these ion-conducting polymers that are used for thermoelectrics have the advantage of low thermal conductivity, but the ionic conductivities and ionic Seebecks are very hard to measure, therefore being very low and unreliable. Therefore, poly-2-dimethylaminoethyl methacrylate methyl chloride quaternary salt dissolved in methanol was chosen for studying the contributions of ionic conductivity and the ionic Seebeck because of it being a simple system. The polymer structure consists of a polymer backbone containing a charged side group and counterion, whereby the latter is the only mobile charge carrier involved. The incorporation of ferric chloride into the polymer matrix was studied in order to quantify the changes to the ionic Seebeck effect and the ionic conductivity.